Alright, good day everybody. So today we're going to talk about intermolecular forces. At this point we've done all of the types of intramolecular forces, the bonds that you find within molecules or ionic compounds. And now we're going to talk about something called intermolecular forces. The first thing that you should really be aware of is that intermolecular, inter means between. And so we only see this when we have molecules, which only occur in a type of substance called a molecular substance. So we only see this when we have covalent bonds. So this is only in substances where we have covalent bonds. Now, what is an intermolecular force? Well, first of all, some background. It's much weaker than you're going to find a regular covalent bond. Intermolecular forces are not bonds. Even though the biologists kind of ruin this and they actually call one of the intermolecular forces a hydrogen bond, it's a misnomer. It's an intermolecular force. Now, what do we do with intermolecular forces? Well, their main purpose is to try and look at the boiling points and melting points of substances. Generally, the stronger that you have intermolecular forces, then the higher the boiling point and melting points. And this is because when you boil a substance or melt a substance, some of the intermolecular forces are broken. For example, if I were to have here like a solid would be bound together like this, and I'll just draw a quick one here. And each line here would be an intermolecular force. So here in my solid, I have 4 IMFs. But when I make it into a liquid, I break some of them. In this case, I only broke one of them because I have so few. And so here I have 3 IMFs. And when I'm a gas, well, now all my 4 molecules are spread out. And I have 0 intermolecular forces. When you melt and you boil something, you break IMFs. This is different from breaking a covalent bond, and I can't stress that enough. Covalent bonds, you would decompose the substance. When you break an intermolecular force, it's a physical change. It is not a chemical change. Now, all the intermolecular forces that we're going to look at are based on attraction. You'll remember in the first part of this chapter, we were drawing partial positives and partial negatives. And so the partial positives and partial negatives that we drew are what going to attract molecules together. And I'm going to go through each type. The first type of intermolecular force is something called an ion-dipole. And this is an attraction where you have an ion and a polar molecule. We mostly see this when we have aqueous solutions. And I have a good picture of this on the next page, and here it is. So this would be, for example, my Na plus, and this would be my Cl minus. My Na plus, if this was water, this would be the oxygen. Let me just do that in white, actually. So this would be the oxygen right here, attracted, and here would be the hydrogens. And so the Na is attracted to the negative. On this side here, we have our H's and our O's, and it's attracted to the Cl minus. Opposites will always attract each other. That's what causes these to stick together. Now, when I dissolve salt in water, that salt breaks apart, and that salt then is attracted to the charges of the water. Now, this isn't as strong as an ionic bond, but water is a pretty powerful molecule, and it can break apart these ionic compounds nicely. Sometimes, though, you'll put a salt or you'll put some substance into water and it won't dissolve. And that mainly has to do with the fact that these forces that form just aren't strong enough to pull those particles apart. All right, the next type of intermolecular force is called a dipole-dipole force. A dipole-dipole force is where you have 2 polar molecules attracting each other. So what would this look like? Well, if I were to have something like, HCl. Well, if I look up their electronegativities, H is partially positive, Cl is partially negative, and this is a covalent bond that I'm, making thicker here. But what would this look like in an intermolecular force? Well, there would be another HCl over here. And this H is partially positive, and this Cl partially negative. And so what will they do? Well, they'll attract each other. This H and this Cl will attract each other. That attraction will keep them together. I could do this again over here with a Cl and an H. And I could have my positive and my negative. And then again, I could draw in green here my attraction between my H and my Cl. Now, when we look at molecules, the more polar they are, the more that they stick together. And so if I were to look at different molecules, like I were to look at HF, I were to look at HCl, I were to look at HBr, I were to look at HI, what you'll tend to see with this is that this has the biggest partial positive, partial negative, and this has the smallest partial positive, partial negative. This would have the strongest IMF. In my notes I put IF, but IMF, same thing. And this would have the weakest. This would have, up here, the top, the strongest IMFs would have the highest boiling points. So if I try to boil these four substances, the first one to boil at the lowest temperature would be the one with the weakest forces. As the molecules have stronger forces, it takes more energy to break them apart. Here's just showing you a nice dipole-dipole using their blob structures here. You have the negatives and the positives and how they all attract each other. They also show the repulsions. It's from an AP textbook. They're trying to give you a more full view of what's going on. Now, the next type of intermolecular force for chemists is so annoying because the biologists got in here and they named it something called hydrogen bonding. Hydrogen bonding, all that it is it's just a type of dipole-dipole. On average, this type of dipole-dipole tends to be about 10 to 50 times stronger than a normal dipole. And they call it hydrogen bonding because it always involves hydrogen. This is, again, a special type of dipole-dipole force. And it always involves hydrogen, and the hydrogen has to be bound to one of these three atoms: fluorine, oxygen, nitrogen. The way I remember this, unfortunately, is by saying that hydrogen likes to have fun, F-O-N. So, we see hydrogen bonding here where we have HF. We see hydrogen bonding here where we have something like H2O. We see hydrogen bonding when we have NH3. All of these have H bound directly to HF, HO, HN. For example, if I were to show you HCl, this is not going to be considered to have hydrogen bonding. The thing is, though, is that hydrogen bonding doesn't look any different than dipole-dipole. It's just stronger. So again, a hydrogen bond is just a strong type of dipole-dipole force. It has the same idea, the positives and the negative attracting each other. And I can show you that on the next page. We'll come back to why this is important in a second. But here's showing you the hydrogen bonding. It looks identical to what I drew on that other page where I had HCl. If I drew that over here, HCl would be like this, and I would show it with dots this time to match their type of drawing here. This is my hydrogen bond right here. It is just a strong type of dipole-dipole. This makes molecules that have hydrogen bonding have the highest boiling points of other substances. If you think about water, for example, has a boiling point of 100 degrees Celsius. You look at other molecules that are around the same size as water, and they're much, much lower. And this is because of water's hydrogen bonding. This gives water this really unique property of having a high boiling point, and that makes water extremely special. Think about what you are mostly made of. 70 to 80% water. If that water didn't have those strong cohesive forces holding it together, then you'd have a situation where the water would boil and we wouldn't exist. Here's another picture of water, and this is showing you a network of hydrogen bonds right here, and I'll just circle it. And it's showing you how they form this array, and that array has a crystal structure. And that crystal structure shows you that it is in the shape of a snowflake here. Again, hydrogen bonding is weaker than covalent bonding, but it's the strongest of the types of intermolecular forces. Why is hydrogen bonding important? Well, things like the boiling point of water that I just mentioned. Things like DNA structure and RNA structure. You remember DNA, they talked about the double helix and about the pairing up of the base pairs. Those base pairs are paired because of hydrogen bonding. All right, the last type of force that I want to talk to you about today is something called London dispersion forces. Sometimes this is called van der Waals forces. And this is a type of force of attraction between nonpolar molecules. So far, dipole-dipole, hydrogen bonding, ion-dipole, they've all involved polar molecules. But what if you have nonpolar molecules? They can still stick together. They can still form liquids. It's just that the forces are very weak. And so what happens is the nucleus from one molecule is going to attract electrons from an adjacent molecule. And in an instant, they're going to become attracted to each other. You're going to distort out their electrons. They're going to be what's known as an instant dipole. The two molecules, or atoms, they attract each other for an instant. They stick together. They liquefy. But it's very, very weak. And so molecules that have these types of London dispersion forces don't have very high melting points or boiling points. They tend to exist as gases. What does this actually look like? Well, this is showing you what it looks like over here. So here's two helium atoms. They have no attraction in A over here. But the nucleus of this helium over here starts to attract these electrons, and you get distorted, and you have a dipole. These stick together. Now, most samples of gases have, 10 to the 23rd, 10 to the 25th atoms or molecules. There's a lot of them. This on-off switch of them sticking to each other again and then not sticking and then sticking happens, and so then they will liquefy. But you need to generally lower the temperature quite a bit. If we look at, things like carbon dioxide or nitrogen, these have boiling points around, minus 150 degrees Celsius, minus 180 degrees Celsius. When 2017 comes, January, I'm going to get you some liquid nitrogen. I'm going to show you what that looks like. You're going to notice it's cold. As a liquid, it's really, really cold. It looks like water, but it's much, much colder because we had to cool it down and pressurize it in order to get it to become liquid nitrogen, not gaseous nitrogen. One thing I want to talk to you about with these London dispersion forces before we stop, and that is this statement right here, which I'm going to highlight, and that is the factors. If we want to get the intermolecular forces to take effect, we need to get the molecules close. And the larger the molecule is, the higher its boiling point. And I'll show you that right here really quickly. If we look at fluorine, chlorine, bromine, iodine, if we look at these, fluorine, F2, it is the smallest. It has the smallest radii. So it will have the weakest forces. And because of that, it's a gas. By the time you get to iodine, it's the largest. So it has stronger forces. And so it's a solid. Now you'll also see that when you go down the group 18 as well. If you look at helium, you have to cool it down to 4 Kelvin to liquefy it. Xenon, all the way at the bottom, radon, you have to cool it down much less in order to liquefy it. Has a higher boiling point, has stronger forces. So do me a favor, take a look at this flow chart. Make sure you know this stuff here and that you're able to go through this flow chart, and we'll talk about this in class. The last slide set for this chapter is bonding in solids. All right, thanks so much for watching. Have a great day.